Well, welcome back. I hope you all had a wonderful afternoon somewhere. I'm looking forward to hearing about all your adventures since some of us have to work. But this evening, I'm going to start off talking about main sequence binary populations, and this remains in the spirit, in a sense, it's the last lecture in the spirit of what is it we're trying to produce in these star-forming regions. And as I was working on this and some others this afternoon, I started to finish it with this question, and then I thought, why am I answering this question? You're the students. So, at the end of this lecture, I'm going to ask you to talk about in what ways are binary populations relevant to this school, to the dynamics of young clusters and associations. All right? And also recall the count of 100 questions as well. Okay, so there's a lot of things that have to be going on in your mind right now. All right, so let's get started. Rough overview. I'm going to talk first about the field solar type binary population. Then I'm going to talk about the field massive star binary population, where the concept of the field is perhaps a little confusing. I'm going to talk about open cluster binary populations. Then I'm going to just make a few comments about some broad points about binaries that may or may not be relevant to this school. I'm not quite sure how this will play out. And then I'm going to turn it over to you, okay, for the summary. All right. So beginning first, I want to emphasize that we're talking, for the moment, about solar type stars. Now, solar type means anything. Where have you been? Solar type, roughly speaking, means anything from perhaps half to 1.5 solar masses. So we're not being strict about solar mass stars per se, but solar type stars in that domain of mass. There's a long history of studies of binary populations in this domain. I could actually keep right on going down through Ipik all the way down to Herschel. But I do want to mention, too, before the current one, Apton-Levy in 1976. I think Helmut App really is the one who sort of put on the map the idea of systemic, comprehensive studies of binary populations of a particular class of star. It was a real breakthrough paper. And then, of course, from nearby Geneva, the paper by Antoine Duquesnoy and Michel Mayor was really just a major step forward in terms of caliber of the data, quality of the analysis. It really raised the bar. And if you go and look at the references to this paper, you'll see some 1,500 references. So, I mean, it really was a spectacular piece of work. Still is, but as time passes, the techniques do improve. And just recently, this paper was published, which I'll draw from, which I suspect, unless problems are found with it as people explore what they've done, will replace these two and become the standard reference. So to give a sense of what all of these studies did, and this is specific to Ragahaven, they took 450 stars from the Hipparcos catalog out to a distance of 25 parsecs. So their attempt is to be volume limited. And this is how they define solar type, B minus V between 0.5 and 1, F6 to K3, dwarfs and subdwarfs. So that's their operational definition of what solar type means. And then they applied to it, and of course the author list is very long as a result, just essentially every possible technique other than space in order to find every companion that they could, including, this is of course the very new technique compared to Duquesnoy-Mayor, the optical interferometry at Chara, speckle, including infrared, multi-epoch images looking for wide common proper motion pairs, radial velocities, and the literature is still very, very relevant. It's the beautiful thing about binary stars. They don't go away once you discover them. So they put all that together.
Hello?
Yes, please.
What's speckle?
Say, what is speckle? Yeah. Oh, there's a lecture for you. Okay, so essentially what speckle is from the ground, if you take very, very rapid images, what you do is you freeze the atmospheric seeing. Then through a Fourier transform technique, you take all those images and combine them together. So with any luck, you've got the diffraction limit of the telescope. So the idea is to actually get rid of atmospheric seeing. I have never done it, although I have collaborated with someone who has done it. It's a wonderful thing. It's called speckled because if you Fourier transform an atmospheric image, you get a set of speckles, if you actually look at the image. So to get a sense of just the level of frequency of multiple systems, the single stars in this case were roughly 56%, which is a little more than Duquesnoy-Mayor had expected. Typically, the numbers that have been thrown around have been that 55% or so of the stars are multiple since Duquesnoy-Mayor. Perhaps that was a bit of an overestimate of their incompleteness. But roughly speaking, 50-50 is what we're talking about. Half are single and half are multiple. I don't want to bend your minds around all the different ways that you can count multiplicity. This is the most simple way. You look up in the sky and there's a star. And that star may be a binary, maybe a triple, maybe a quadruple. So that's the sense of this. It's not companions per star or anything like that. It's simply sort of number of systems of each type. So we have higher order systems at about 10%, binary at around a third, and single at about half. One caution that, I remember I made a caution this morning about radii of clusters. There's a similar caution in the literature about binary frequencies. As I'll show, let me make the caution with this picture. Oh, please, yes.
Does a system, for example, a quadruple system counts for 1 stars you see or for 4 stars you see?
There is a star of the 454 that has 4 stars as part of its system. Okay. So a very important result, and from this will come the caution, is this period distribution. So this is the period distribution all the way from, this is in days, log of days, down to sub-day for a couple, out to 10 to the 10th days. So they've been observing this one for a very long time. That's a joke. They don't have any orbits of 10 to the 10th days. No one is that old in this world. That's a statistical orbit. Just making sure that you're listening. The caution that I want to make is as you look in the literature about binary frequencies, you will see many, many quotes about binary frequencies. And far, far too often, they don't tell you which part of this distribution they're talking about, right? In a sense, the meaningful binary frequency is the integral over this distribution. But very often, papers will quote a certain frequency, and implicitly what they mean is the frequency of binaries that they found using their technique. Well, any given technique, in fact, as I'll show you here, any given technique is only a part of this distribution. And you must be very wary about that when you start comparing results from different papers. Or perhaps it was a photometric study that's looking at stars that are elevated above the main sequence, and they'll quote a frequency. Well, what does that frequency mean? They clearly don't have all stars because the ones that are elevated, all binaries, the ones that are elevated are those with roughly more equal mass companions. That's not a criticism of them. I'm simply saying you have to be cautious about comparing frequencies among samples. Just in terms of technique, down here is typically radial velocity at less than maybe 10,000 days. It is sobering when I did have an orbit of 10,000 days. That told me I've been doing this for a long time. These are resolved orbits in here and common proper motion pairs out here. And of course, what's exciting today, not so much about what we're talking about here in populations, but just we're getting overlap now between the interferometers and the radial velocities. And that allows us to get tremendous astrophysics on the stars. But that's not terribly relevant for the populations. So roughly speaking, the mean period of a binary is about 10 to the 5th days, or 300 years. Okay? This Gaussian distribution is very similar to what Duquesnoy-Mayor found, shifted a little bit to longer periods. They've had a higher detection rate out here. But this seems very solid over the course of at least the last 20 years. Typical separation is around 50 AU. But again, I want to drive home this range. This is what, 10 orders of magnitude in period. So when you're talking about binaries, you've got to specify what you're talking about. These means don't really in themselves even mean a whole lot, except perhaps that in this domain you have the most binaries. Beyond that, you have to be very careful with who you're talking to. This is what now become a fairly classic period. In fact, figure, there's a meeting that happened in Switzerland 25 years ago, which has become known as the E log P meeting. It was in honor of Roger Griffin's 100th orbit. This is a plot of orbital eccentricity versus log period. And you can cut it a number of ways in terms of its interest. Usually what's most striking is the fact that everything lower than a certain period, which I'll give in a second, tends to be circular, or physically circularized, by tides presumably. And then out here you're looking at the distribution of eccentricity, which I'll show you in a marginal cut shortly. But I do want you to notice that nature very rarely, if ever, makes circular orbits unless they are circularized. Okay? Circular orbits are not favored, and in fact, very, very high orbits are not favored, which is a bit unexpected for a relaxed distribution. But this figure has a great deal of physics in it, and I'll be coming back to it. For the field, this circularization period, this longest period circular orbit, is a period of about 12 days. Okay? This is, in fact, the orbital eccentricity distribution I was just showing you. As you can see, it's very broad. You may be saying, but Bob, you said there weren't any circular orbits. Well, there aren't any circular orbits. This bin is from 0 to 0.1, and these are all greater than 0.05 or so. Nature is wonderful when it comes to circular orbits. When they're circular, they're circular. Okay? And you might wonder why they made such a complex figure, and basically it's because of this figure from Duquesnoy and Mayor. Duquesnoy and Mayor argued that for intermediate periods, the circularization period to 1,000 days, it was a Gaussian-like eccentricity distribution, and then they made this very provocative statement that for longer than 1,000 days, especially when they corrected for incompleteness, it looked like this line. This line is known as the thermal distributions of eccentricities. Essentially, it's a relaxed distribution. If you have a stellar system that goes through a full, complete relaxation of encounters, then the angular momentum distribution will lead to a line that is f of e equals 2e. And they thought they might have seen it, even though in fact there's no reason why the field should be relaxed. If it were, I assure you, we would be spending a lot of time at this meeting explaining it, because it would have to happen early on at high densities. But in fact, every indication is that that result, at least for the moment, has gone away. There's really no indication of a relaxed distribution here. It's far more like a broad Gaussian, which presumably is primordial. Okay? There we are. In terms of the mass ratio distribution, this is a figure out of their paper. I'm not going to speak about all of these figures too much. I want to focus on this one. You'll notice that the mass ratio distribution is really largely flat here, with two notable differences. One is there seems to be a deficiency, which they claim is real, at small mass ratios. And second, there seems to be a set of what are typically called twins, a preference for equal mass systems. Both of these seem to be, if they're real, in the short period binaries, the spectroscopic binaries. And since these are the most easily detected in the spectroscopic binaries, it presumably is a complete sample. This is a little more difficult. I only bring this up because historically, and you're going to see this throughout the talk, this question of whether there's a preference for equal mass systems has been around for as long as I have. And that pendulum has swung back and forth as to whether they're there or not. They make a very large difference in our theories of star formation. If there's a preference to make equal mass stars by whatever process, that's very significant. That has to be explained. And similarly, in fact, this is a brand new result. If there's a deficiency here, that needs to be explained. But I'm only in a sense cautioning you that I have seen this come and go and come and go over the years. It seems to have returned. Duquesnoy Mayor didn't find it, and I'll be interested to see how long it survives.
What range of masses did they observe?
Well, let's see, that was in the opening slide. It's about,
F6 to K3.
pardon me?
F6 to
Right, but he's asking for the masses of that, so
I'm a theorist.
yeah, you're a theorist. Perhaps 0.6 to 1.2, 1.3, something like
My
that.
point is that you wouldn't expect to find very low mass ratios if you're observing solar-type stars, right?
You mean technically?
Yes.
Their claim is that they would have detected these. Again, these are in the spectroscopic binary system, and stars are actually, even very low mass stars, when they're short period, have a tendency to swing the other star quite a bit, and they really are detectable. If it was photometric, I would be very concerned. Your point's well taken. Mind you, this is the first time it's ever been mentioned, so it needs to be confirmed. One problem, of course, with large studies like this has taken a decade, is that confirmation takes a decade. This is a paper by Madalena and Michael, so I wanted to give it a bit of a highlight here because they too have been looking at these secondary mass ratios. What they've done here is this is a secondary mass ratio plot of, in this case, a G-type sample, and in this case, an M-type sample. In this case, it's an imaging sample, so it's not the entire domain, the entire spectrum of periods. And essentially what they're doing is they take an initial mass function, the one of Chabrier, and they do a Monte Carlo analysis. I'm sure saying they do it means Madalena does this. And Michael sits back and says, well, let's see how this goes. So Madalena has done a superb job of a Monte Carlo analysis drawing from the field IMF to see whether or not this secondary mass distribution can be explained by simply a random pairing from the field IMF. They find that that is 0.07% likely for the G stars. For the M stars, it's perhaps 2% likely, and you'll soon see for the A stars, it's very, very small. So their essential conclusion is that these secondary mass ratio distributions that we're seeing come from the process of binary formation. It's not simply a pairing of stars. So let me summarize what we have here at this point. We have a frequency of binaries, of multiple systems actually, around 44%. A period distribution that looks log normal with a mean period of 300 years. An eccentricity distribution, orbital eccentricity, that looks uniform or a wide Gaussian. A mass ratio distribution that I think certainly appears uniform. The twins I will hold my opinion on. Blue means that I believe it. Black means we'll see how it goes. Okay? So let me stop there. That's sort of the core, that's going to be the best sample that we've got, solar type binary populations. Any questions? Okay. Now the OB stars, what a mess. Okay. The massive star binary population, and of course there's a whole range of stars. I'm going to define them as earlier than B3 because this is the work of Brian Mason at Georgia. And they're all ZAM stars, so zero-age main sequence, so they're all greater than 8 solar masses or so. These are the kind of frequencies that Brian has found, binary frequency. He separates them between those that are in clusters and associations and those OB stars that are in the field, which essentially just means they have no other compatriots, and then the runaway OB stars, which is another story, although a fascinating one. And right off the bat, you can see that the frequencies are much higher. 57% spectroscopic, 57% resolved. Some of these are triples, so they don't simply add up. A total frequency of 75%. That's almost twice what's found among the solar type stars. And I'll say that this goes all the way back to an unpublished paper by Adrian Blau that is probably the most circulated unpublished paper ever. We all have a copy of it, in which he claimed that of the O stars that he looked at in the early 60s, something like 80% were spectroscopic binaries. And I'll be honest with you, I never believed it. It was just no reflection on Blau. It's a reflection on how difficult it is to measure radial velocities of O stars, which I'll show you in a moment. Nonetheless, over and over and over again, ever since I got that paper, that the result of high frequencies seems to continue among these OB stars. And the whole dynamic range hasn't even been figured out yet. As you can imagine, finding low mass companions, photometrically in particular, imaging, is very difficult for OB stars. And this range just technically has not even been explored yet. So in principle, these should all rise. Please.
For these OB stars from all the super WASP and so on transit surveys, don't you get a number of transiting low mass companions to OB stars, something like that?
In which surveys?
Like super WASP or HAT or something?
I suppose. To be honest, I haven't seen results from that. So that would be a wonderful thing for you to follow up on for tomorrow. No, it's a very good thought, and I don't know. This is just a bit of an aside because it was mentioned with respect to Gaia this morning how Gaia was working in the red, and that was an inhibition for OB stars. I just want to be very clear that measuring spectroscopic velocities for OB stars is very difficult at the kind of precisions that we need. Tomorrow, if I have time, I'll show you what a spectrum of the sun looks like. And the main point is it's a technical phrase, there are a gazillion lines in the sun. When you look at an OB star, this happens to be in the H delta region, this happens to be around the Balmer series, there's just nothing to work with, right? There are the broad lines, and these broad lines are difficult to centroid on at levels of 1 kilometer per second. There are a few narrow lines, but of course I have selected here by selection, because I wanted to show you their spectra, the low V sin I stars, the low rotation stars. Most OB stars are rotating very rapidly. These are long gone. I mean, they're just so flat you can't even see them. And even the Balmer lines start to broaden out. Trying to measure velocities to 0.5 kilometer per second on that type of signal, and there's so few of them as well, is very, very difficult. I've tried it my entire life, and I honestly have never really believed that I knew my precision. And if you don't know your precision, you're sunk. Because if you don't know what your precision is, then you can't know what variations are real. And if you happen to be optimistic about your precision, your spectroscopic binary detection rate gets very high, right? So all I'm getting at is this is a very difficult domain and a very important one for those of you who are willing to pick up the torch. This is a nice study by Sana and Evans, just again basically showing that the spectroscopic binaries in the OB stars, this is a literature study, looks like it in itself is roughly twice that found in the solar type stars. Another case of arguing that the frequencies are high. But again, I remind you that this study is only looking at this much of the entire distribution. So, you've got to keep that in mind. Now, I'm going to talk a little bit about orbital parameters, but I'm being very careful here because this is the sample, and I don't write this down, my heavens. But I'm just trying to point out only 40 or 50% of the spectroscopic binaries have orbital solutions. In other words, somebody said the star varied in velocity, but nobody went out and found a Keplerian solution for it. And in my own world, if I don't have a Keplerian solution, I don't believe it. So that said, let me at least show you what has been found. So among massive star binaries, this is the accumulative plot of the period distribution. And this is uniform, and you'll recall that in fact, I may have it. No, I don't. The solar type was Gaussian in log p. So you say, well, this could be a Gaussian, a cumulative distribution of a Gaussian. But notice, the 60% point in this distribution happens at 10 days. 60% of the binaries have periods less than 10 days. If true, which is my common theme here, but if true, that's amazing. That's absolutely amazing. It's 60% of all binaries with orbital solutions, which are primarily spectroscopic. So that is the catch, right? Because we have a situation where, because of the difficulty to measure precise velocities, it is hard to get long period systems because they have the lowest amplitudes. And so, it's the hardest to detect and get orbits for. I'm not sure I believe it, Kathy.
But what about imaging pairs that are right at that diagram? They're not included.
Well, they don't have orbital, they don't have periods. Yeah. The eccentricity distribution, you'll recall that it's a broad Gaussian, maybe nearly uniform for the solar type. I could believe that this distribution, remember eccentricity, if it's not period dependent, doesn't care about the biases we were just talking about. I could believe that this distribution is comparable to the solar type. It starts off with 25% of these orbits being circular, but of course that may simply be because so many were short period. This is the E log P diagram. And you'll notice, for those of you who are theorists, interested in stellar astrophysics, you'll notice that the period of circularized orbit among the A stars goes out to 10 days. And in fact, among the OB stars, you could argue it goes out to 13 or 14 days. That shouldn't happen. Right? Our whole theory of circularization, to a large extent, has to do with dissipation within the convective envelopes of stars. OB stars don't have convective envelopes, and so this comes as rather a complete surprise. But you also notice that there's no clean cut here. Look at all these stars of short period that have high eccentricities, and then look at this stuff out here. This is because velocities are hard to measure. This is basically lousy orbits, right? I would forget everything from here on over. And so, but this looks pretty solid in here. So if you're interested in stellar astrophysics, which means if you're interested in the interiors of stars, the tidal interactions going on in these binaries is a way to probe the interior. The mass ratio distribution looks very uniform. There's no evidence of twins, and it too is clearly not an IMF pairing because the IMF is not uniform. And this, again, is Madalena and Mike's work. And for A stars, they too find that the companion mass distribution is not like the IMF. So to summarize, because I know it's hard to keep track of all of this, for OB stars, we have a higher percentage of frequency. We may have a very high frequency of low period. I'm not sure if that will survive. We need more orbital elements to find out what the eccentricity distribution really is. I suspect that the mass ratio distribution is uniform. Remember, Blau said there were a lot of twins. Now, at the moment, there aren't twins. We shall see. This is a wide open field for you. This is a place where you could make a major mark. And then last but not least, I want to talk a little bit about the open cluster binary populations, because they too are part of the product of this school. And I'm going to talk about solar type, hard binary, and I'll explain that tomorrow, but I'll briefly explain it now, binary populations, in the cluster M35, which is a young enough cluster that it's quite plausible that what we're seeing is a primordial population, an initial population. The population that ought to go into N-body simulations, for example. Hard binary, just very, very briefly, as a binary orbits within this cluster, it will encounter other stars. During that encounter, if you're a hard binary, the typical result is that the binary itself will shrink, giving up energy to one of the three stars in the encounter and ejecting that star with higher energy. It's an energy source for the cluster like nuclear fusion is for a star. And I'll talk more about that tomorrow. But the reason that I focus on these, this is a classic case of second guessing. I focus on these because these are the things that drive the dynamic evolution of clusters. They also happen to be technically what I can do. It's a nice mix. It worked out well. So again, the data are going to be gorgeous, not just because they're mine, but because they're solar type stars. We have a binary frequency and period distribution here. And let me give you a sense of scale so you know what you're looking at. This is our binary population. This line, this field line, is that line. And you can see that within the domain out to about 10 to the 4th days that we can do with spectroscopic techniques, the agreement looks very, very good between here and here. So this is the field. This is a young cluster. Not an embedded cluster, not a proto-cluster, but a young cluster. This is the eccentricity distribution for this young cluster. This is the field. This is that relaxed population that I told you was not seen in the field and is also not seen in the cluster. And again, you cannot distinguish the two. There's a hint, and I'll come back to this later, that there might be a peak over here, but that's entirely because of incompleteness corrections, and that's something that you need to worry about. But basically, you're looking at a broad distribution, more or less Gaussian-like, just like in the field. The E log P diagram is essentially identical with one notable difference, which matters a lot to me. The circularization period is 10 days, whereas in the field it was 12 days. Good. We're going to come back to that. Young cluster, 10 days. Old field, 12 days. You can already see the story. But otherwise, very similar. Mass ratio distribution. Again, it looks fairly flat. This is an IMF. I would say it looks fairly flat. And again, I would say it's indistinguishable from the field. No sense of that drop at low, well, indistinguishable except there's no twins. And so roughly speaking, recognize that we can only work in the spectroscopic, the less than 10,000 day domain. The frequency is like the field, the period distribution is like the field, the eccentricity distribution is like the field, the mass ratio distribution is like the field except for the twins. Every indication is that this young cluster, which is not very dynamically evolved, is very much like the field stars. Okay. Okay. Let me digress just a little bit because I know quite a few of you are working on cluster dynamics, as I found out at dinner yesterday. This is a 7 gigayear-old cluster, so this has gone through many, 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 many times of relaxation. This is the cluster I showed you this morning, where I showed you that all the low-mass stars were gone. Okay? So what's the binary population look like? It's kind of interesting, actually. The total binary frequency in this cluster is actually unchanged from that in the field after 7 gigayears of evolution. There's mass segregation, right? You can see that most of the binaries are in the center as compared to outside, but the total frequency is essentially unchanged from 10 to the 7th years of dynamical evolution. The period distribution is largely unchanged. This all came as a great disappointment to me, by the way, right? I was looking for signatures of dynamical evolution here. The period distribution is, the eccentricity distribution is largely unchanged with one notable thing which shows you how I'm grasping at straws. You see this peak out here. If in fact you have dynamical interactions going on, then you preferentially produce high eccentricity binaries. I'd like to think that that is the result of dynamics, in part because most of those high eccentricity binaries are in the core, where you'd expect the dynamics to be happening. So we may have a hint there of it, but boy, it's just a hint. The circularization diagram looks much the same, except 15 days. That should make you all very happy. Okay? And the one thing that is different, curiously enough, this, if anything, should give you some pause about this entire IMF study, or a companion mass study. This one has got twins, if you want. Certainly, it's arguably not flat anymore. It certainly looks like it's rising to smaller separations. The interesting thing about the twins dynamically is that when binaries go through encounters and do exchanges, like I'll show you tomorrow, preferentially the two most massive stars stay behind. So again, I would love to argue, and I would have argued from Duquesnoy-Mayor, that that's dynamical. Now these guys have got twins, primordially. I don't know what I'm going to say. All right. So let me stop there. That's populations. Any questions?
I didn't quite get the hard binary part, I'm sorry.
Yeah. Wait till tomorrow. I'm going to explain it really clearly tomorrow, and it's not critical right now. So.
Are the twins preferentially in the core? I know your binaries in general are, but is there a special kind?
That's a good question. I actually don't know, Kathy. That's a good question. I'll find out by tomorrow, because we got a time lag to my student.
There's a paper by Jenny Patience from Harvard from 2002 that shows the clusters alpha per and precipate seem to have an overabundance of binaries in the range 10 to 1,000 AU compared to the field.
Yeah, I know. My comment is that it's high time somebody do it again. It's been 20 years. Right? I think that was a very important paper when it came out, but it hasn't been verified, it hasn't been further studied. It would be very important to do that. At the time, they did the Hyades and Price because they were close, but we're now at a place where you could do many, many clusters in the same way. I suspect someone is. Okay, a couple of sort of global points here. First, binary frequency as a function of stellar mass. This is all the rage in the theory world, and I think it's probably true. Most of the studies among very low mass stars have shown relatively low binary frequencies. You saw that the OB stars tend to have high frequencies. This is the one I really believe, that's the solar type. So there's a general sense of an increase in binary frequency with mass. And that's something that needs to be explained either through the star formation process or through the dynamics process of young regions. And I'm sure Kathy will talk to that.
Bob,
Yes?
just to highlight the point you raised, shall we say this multiplicity fraction is over mass ratios of 1 to 1 to 1 to 10 and integrated over all separations?
No, it's mostly based on imaging studies. So it's down to more like a few AU to all separations. So it doesn't have the spectroscopic binaries in it to a large extent. This one does. And in fact, you'll remember in Matthew's paper, he actually lowers this point in order to make the comparison. It is over the sweet spot. It's over the heart of the binary distribution. That's absolutely correct.
Yeah, I'll actually talk a bit about the low mass star tomorrow.
Okay, good. Please.
Is it because in the field we just talked about the solar type primaries more or less, but if we look at the separation distribution for lower mass primaries and high mass primaries, we see that the separation distribution is slightly different.
Is what?
Is slightly different, right? Is it picked at different AUs or not?
Well, I think you've got a sense of my opinion for the OB stars and how well we know that period distribution, which I think is very poor. I presume you're talking about the A stars when you go to higher mass? Oh, I thought you said the higher mass ones.
No, sorry, lower mass.
Yes, when you go to the lower mass, the period distribution seems to be different from what I understand. I haven't actually worked in that myself. Well, you probably looked at it as much as I have. What do you think?
No, it's just that I was thinking that maybe, I don't know if it can affect or not this kind of study, but if the separation distribution for lower mass primaries is peaked towards lower mass binaries, then you would expect to have a lower frequency.
That's correct.
Because you cannot see them with imaging.
That's exactly correct. Yep. And I must confess, I don't really have an opinion on that.
I do.
Yeah, Neil.
I'll talk a bit about this tomorrow. And there's two things going on. First of all, the maximum separation for stable binaries decreases as you get to lower masses, which brings down the frequency. Also, there is definitely much more of a tendency towards equal mass systems in the low mass binaries, and that's really incontrovertible. It's not that there are detection limits there, because when you're looking for the imaging, you have the big advantage, you've got a very faint star, so finding a very faint companion is actually easier. You're not getting blasted out by an A star. So we're on pretty solid ground there. There really is a trend, both in maximum separation and in the mass ratio distribution as you move down the main sequence.
Good.
You can, nobody, I don't claim to understand why. I just present the data.
Wim, please.
Does this binary frequency depend on metallicity?
Say again.
Is there any dependency on metallicity?
That is a very good question. When you go into the halo population, when you go into dramatically different metallicity populations, like the globular clusters, for example, there are globular clusters out there which have remarkably few binaries. And at one time, we thought that was actually a systematic metallicity effect. Turns out not to be consistent across all globular clusters, and I imagine Neil is going to talk about that as well. So I think the answer to your question is yes, but I don't really think that we understand it yet. The thinking has always been, as you go to low metallicity, you lower the opacities in the natal material, which lowers the fragmentation conditions, which could affect the binary formation. So there's always been this sort of theoretical desire or hint.
And
That-
there's no clear distribution.
And there's, well, first off, of course, for low metallicity, we don't have any of this, right? So it's a little hard to get any dynamic range on this, right? Are you going to talk about this, Neil?
I think a bit, yeah.
A bit?
And
Okay.
The other thing to remember is that these are field star surveys. I'm going to eat up your time, but and in order to do these observations, you need a large sample of field stars subdwarfs, and there just isn't a large sample of subdwarfs until Gaia comes in and tells us where they are, because you need the distances and so on. And the local halo density is about 0.1%, so there are very few nearby halo stars to do all the kind of stuff that Bob's talking about with the local G stars. And then looking at globular clusters, you can look at the double sequences for near equal mass binaries, but you're really sampling a subset of the population there.
But is it relevant to look at globular clusters because these are not going to be primordial?
Right. Oh, I mean, the hard ones probably are. Yeah. I'll tell you what, this evening, since you're going to talk tomorrow, I'll take your time back. Now, I'll take a look at the Carney and Latham papers and remind myself what they said so I can answer your question better. Yeah. The alignment of angular momentum is something that Kathy asked me to talk about briefly. I was going to talk about it on Wednesday, but I'll briefly mention what we know. There's this study in 1994, notice 1994, which really hasn't been well updated and should be. Basically, what they were looking for was the alignment of binary planes with the triple planes. And a small delta I suggests alignment, and a distribution here suggests not aligned. And they suggested that around 30 AU, there was actually a switchover between the alignment and the not alignment. And I think that in general, this needs to be done again. I'm not saying there's anything wrong with it. It's just very important. And now with the interferometers that we've got, we can start to actually get into those triples that are in this domain, I think, with more accuracy than we had before. So this is work that needs to be done. Please.
Is the same height axis of the inner binary or outer?
This is both. In other words, if I recall how this is made, no, you're right. Now I see what you're asking. It's got to be the outer. It's got to be, because the inner ones were spectroscopic binaries, and that's how they got the plane. Yep, you're right. I was actually thinking of the next picture when I was about to answer your question. There's an advantage that one gets in the pre-main sequence, which is why I'll be talking about this again Thursday morning, because there's some hope of actually getting alignment of disks. This is known as a coplanar aligned system. This is an aligned system, but it's not coplanar, and this is neither aligned or coplanar. So it allows you this is not a case of a triple versus a binary. This is actually looking at the angular momentum planes of the stars compared to the binary, or at least of the disks around the stars. This is work that needs to be done more as well. We did this quite a while ago, but nonetheless, we do it through polarimetry of the disks, trying to look at the polarimetric angles. And these are the differences in the position angles of the polarimetry. This one is from Monin et al. This is from our work at IRTF. And what you just notice in both cases is that there really is a tendency, even at these fairly wide separations, because remember, a typical disk radius might be of order 100 AU. At least the polarization angles, the position angles, seem to align, suggesting an alignment of the disks. And interestingly, and I have no idea how much weight to put on it, these are the triples in our system. And if any system looks unaligned, it in fact are the disks around the triples. So this is work that very, very much needs to be done. And Kathy, I wish I could put you on more solid ground, but this is what I know. So. Oh, of course, HK tau is a classic case of an unaligned system. Right? Here's a binary. This one's clearly edge on. This one clearly is not. And this is another example of two misaligned jets coming out of essentially the same source. And Bo Reiperth and Hans Zinnecker have made a lot of hay out of suggesting that that's the result of misaligned wide binaries as well. This comes from Madalena and Mike's work. This is a companion mass ratio distribution. And essentially what they're suggesting here is that this power law, which comes from Mathieu and Hillenbrand, is universal. Whether you guys are suggesting it or not, certainly Mathieu and Hillenbrand are suggesting that there is a universal companion mass ratio distribution, which is essentially a power law. This is the combination of all of Madeline and Michael's data, and their suggestion is that it looks like it may fit fairly well across the different regions, quite independent of mass. Okay. Please. You have to ask them. Are those 1 sigma error bars?
Yes.
Actually, Michael, are those 1 sigma error bars?
I'm sure whatever Madalena said.
Alrighty.
If we're done properly for small sample, I mean, I guess it's worth mentioning, there's something Neil sort of drove home this morning. Doesn't look like a good fit, but I mean, given that the error bars are big, you know, it's consistent with being fitted with that, but that doesn't mean that is the right, you know, functional form. I think that's a point with very.
No guts, no glory. And then looking broadly at tidal processes, you could see this figure coming, but it turns out to be an interesting field if you're interested in stellar astrophysics. There is the circularization period for the field. There it is for the halo. Actually, that's Duquesnoy Mayors, excuse me. That should go up there. There's the field, the new field. There's the halo, 188 M67. 6819, you can always put your hand over 1. M35 Pleiades and pre-main sequence. And what's interesting about this is that you can see that you expect that as time passes, you'll be able to circularize wider and wider binaries. And in fact, you do see that effect going on here, but it's remarkably flat over this domain. Zahn and Boucher suggested that in fact, all of the circularization happens on the pre-main sequence when the stars are large and puffy with deep convection zones. They, however, predicted that in fact there would be no main sequence circularization at all, as compared to Vitti and Savigny, who said all of it would happen on the main sequence because of resonances in the interior of the star, and they get the right trend over here, but not the right extent. The reality is, as much as people use tidal circularization in innumerable routines, not the least being n-body routines, not the least being Arces's n-body routine, the data do not agree with any tidal circularization theory at the moment. Whether that's going to be relevant for the pre-main sequence stars is not entirely clear, but remember that every time 2 stars pass near each other, there's a highly dissipative effect that goes on that is relying on the same physics. So we'll see whether Kathy talks about that at all. Okay, so let me summarize then. This is just the same figure again, but I want to really, I mostly want to emphasize this. This is solid. This is, most of the stars Kathy's going to be talking about are going to be solar type or less, I suspect, or lower mass stars. And this is the population. And now the question is, and we have just enough time, is for you to tell me what the implications of this are for this school. What, if you were just going to, if I was going to write on the board here, the implications of binary populations for the dynamics of young regions, writ large, broadly, what type of things would you say?
So binary formation and binary heating in a dense young stellar cluster can be important for providing energy for the whole cluster and relating to the dynamics of the cluster as a whole.
Even when the cluster is only a couple mega years old?
Well, from what I've heard, it sometimes does actually.
I'm going to say that tomorrow. Well said. Okay, so one is its dynamical influence on the small n systems. Okay, we'll talk about that tomorrow more. What else? Nathan, is your hand up, or is it just stretching?
I was kind of going to add a point about the soft binaries. I was going to say they can act as an energy sink, and since the cross-section is so much bigger, you could get that done in a shorter period of time.
Okay. Too many theorists. Okay. What else? Yeah.
Mass and material ratio estimates can be totally off if you accidentally hit the binary.
As we were talking about this morning. Good. What else?
also possible be the reason for those runaway OB stars keep away from them?
Maybe they're the origin of the OB runaways. Now, that has been an idea that has come and gone and come and gone, but I would say it's still alive. And OB runaways may lead to runaway pulsars. You know, I mean, there's all sorts of implications for the OB runaways. But good.
But the binary will increase the interaction.
Mm-hmm. That's right. That's right. Yep.
Models of high mass stars, because if they're always binaries, then formation has to deal with binaries. Then other things like winds of high mass stars, if you always have two high mass stars together and you always get colliding winds, then that can definitely affect the wind properties.
Good. Are you a theorist?
Observation.
Oh, okay, you're giving theory answers, which is fine. Yeah.
Well, the star formation process in general, if there's a specific, like a characteristic mass ratio, like the twins, it's shedding some sort of light into the process.
Say that again?
It's shedding some sort of light into the process.
Into the star formation process itself. Good, good.
Perhaps they could be tied down to stellar evolution, for instance, by the presence of blue stragglers.
Ooh, you're going for an A in the class. But what does that have to do with star-forming regions? But it was a nice try. Any others? All right, well, I want to take from Kathy's time. I'll show you what I just put down real quick before I stopped, and I think you've got them. Certainly, it's a constraint on the star formation processes. I mean, I'm sure Kathy's going to show Matthew Bates's simulations, and whatever beautiful things they may do to populate the field, if they don't make the binary population, then at core, fundamentally, they've got a problem. Certainly, dynamical impact within small n systems. I'll talk about this tomorrow morning. This is one that Madalena and Michael have pushed on. If, in fact, we find out that the pre-main sequence binary populations are different in associations or in clusters or in embedded clusters, that mode which produces the field-like population may actually be the dominant producer of field stars. In other words, they may be a flag or a tracer from where most field stars form. And then this is the one I mean about the observationalists, and I'll close with this point. For those of you who are observers, you ignore the fact that every other star is a binary at your own peril, all right? You figure out the mass of a star and it's actually the light from 2, you're off. If you figure out the spectral type and temperature and thereby write this profound paper on this unusual star, probably it's the secondary, all right? If you look at the rotation distributions of young stars in order to look at the angular momentum evolution, but my God, most of those stars are circularized by this companion that's affecting the angular momentum. You're out to lunch, okay? I could keep going on and on because binaries is what I do. But my point is, up until roughly the mid-'80s, every theory of star formation made one star. Most of them were compared to T tau, which is a triple, okay? Enough said. Kathy?